Hey, Calc kids, here's a little bit about parametrics and vectors and how they go together. So here's a cool parametric curve. I think it's cool. You might not think it's cool, but I think it's cool. So what I'm going to do is the x-coordinate is going to be t squared. And I'm going to subtract 2 because I really want to move this graph to the left a little bit. And then the y-coordinate will be t to the third minus t. So there's that little loop in there. Actually, I'll make that loop a little bit larger. So I'll add a 4t in there. I like that. That's a cool curve. I think we saw this the other day anyway. So I want to make a slider. So I'll just go n equals 0, and that's my slider. And then I want to place a point on this curve, so it's moving around. So I will go a of n, and I probably need to make that a little bit larger so it's easier to see. There you go. And so as time moves, that's actually my time slider. Okay, that's time equals 0. That's where it starts at. And as time goes forward, it kind of goes down and goes up. But what we can do is this is all good. This is all good. So if I take the derivative of this and the derivative of that and divide them, I get the slope of the tangent line to the curve. And I can take the second derivative, and that will tell me that it's concave up or concave down. My guess it's concave down on this part of the curve, and it's concave up on that part of the curve. So we did that a little bit last week, and we'll keep reviewing that this week. But there's this thing that's called vectors. And so here is a vector. This is going to be the position vector. And it's just a vector that will go from the origin to point A. And this vector is nothing more than just a directed line segment or kind of an arrow that points to where the point is located on the curve. And that is my position vector. Now, if I took the derivative of the A curve, so I'm just going to go derivative of A, and I'm going to hide the graph because you don't need it. If you compare the derivatives, this is not doing the derivative like we know the derivative. This is taking the derivative of each part. It's taking the derivative of the x term and the derivative of the y term. And you could easily just take the y term divided by the x term and get the derivative that we learned about last week. But this also gives you the velocity vector, because the velocity is the derivative of position. So velocity is a vector, and I want the vector to start at point A. So it's going to go from A, and then it's going to go from A plus a little bit. So I want it to kind of go in this direction. So that will be the x-coordinate of, actually I think what I can do is I can probably just do this. A prime of n. Oh, and there's my velocity vector. So the velocity kind of gives me the direction, and then it's starting to slowly turn. And velocity, it looks like it's speeding up, and then it's slowing down again, and then it's speeding up because the velocity vector is getting longer. So the longer the velocity vector is, the faster the particle is moving. So it looks pretty short right in there when it's taking that turn. So that's velocity. Now there's one other one. There's one other one as well. So if I took the second derivative of this, so if I go the derivative of A prime, that's the second derivative. And this is going to give us the acceleration vector. So the acceleration vector always has an x coordinate or component of 2, and the y component will get longer and shorter depending on the value of t. So let's make our acceleration vector. This is a vector that will start at point A and will go at A plus little a double prime of n. And it's hard to see it because they're all kind of squished together, but you can see that acceleration. Here's my acceleration vector. I'll make that a different color. I'll make that one that color. And I'll make the velocity vector that color. So when the acceleration and the velocity vector kind of point in the same direction, the particle is speeding up. And when they point in different directions, like right there, they're kind of pointing in different directions, it slows down. So what we can do is, if we just do the derivatives term by term, we can get all this information about the acceleration vector and the velocity. And if I took the length of the velocity vector, that would be my speed. And if I incorporate some integration into this, I can find things about the distance traveled. So, but I want to at least show you that. Kind of a little connection between vectors and parametric equations.